In this video, we're going to look at the subring criteria theorem. This is a useful theorem for figuring out when a subset actually is a subring. And the statement of this theorem goes as follows. We're going to need to let R be a ring, and we're going to let S be a subset of R. And the theorem says that S under addition and multiplication is a subring of R if and only if S has three properties. And these properties are, first of all, S is not going to be the empty set. Second of all, for every pair of elements inside S, we have to have one of them plus the additive inverse of the second one belongs to S. And the third property is that for any pair of elements inside the subset S, R times S will be an element of S. And it's important to understand that this theorem works in two directions. That if we know S is a subring, then we can immediately conclude that S has all three of these properties. But just as important, if we can show that a particular subset has these three properties, then we can conclude that the subset actually is a full-fledged subring. Because this theorem is an if and only if theorem, we have to prove both directions. So what we're going to do first is we're going to look at proving the forward direction. In other words, we're going to assume that S is a subring. Of the ring R, and we need to show S has all three properties. And the proof of this is based on the fact that that S is actually a full-fledged ring. So since S is a ring that lies inside the ring capital R, we actually know a fair amount about it. We already know the following things. From the previous video, we already know that R0 lives inside of S. That was lemma 1 on the previous video. We already know that if a particular element lives inside S, then its additive inverse is also inside S. That was lemma 2 from the previous video. And we know that S satisfies all the ring axioms. And what we actually know then is that, first of all, let's write this as a so. So first of all, the fact that the 0 in R belongs to S is enough to prove that S cannot be the empty set. So the first property, property A, holds. Next, if I have R and S being any pair of elements in S, then I already know that minus S does indeed belong to S, and because S is a ring, R plus minus S is now the sum of two elements in the ring named S. So of course R minus S has to belong to S, and that says property B holds. And finally, we are going to also note this. If little r and little s both belong to capital S, then R times S has to belong to capital S, since capital S is a ring itself, and multiplication is always closed in rings. And so that means the proof of the forward direction is now done. So now what we need to do is we need to turn our attention to the backwards direction. So now what we're going to do is the proof of the backwards direction. And in this particular direction, what we get to assume is that R is a ring, and S is a subset of R with the three properties. And the three properties that we know that S is going to have is, first of all, we know that S is not going to be the empty set. We're going to know that for all R and S inside capital S, the sum R plus minus S will belong to capital S. And the third thing that we know is that for all R and S inside capital S, the product R times S belongs to capital S. And so we're going to now then need to show that S under plus and times satisfies all the ring axioms. So our proof is going to start with going back and looking at the ring axioms. So let's look at the ring axioms. Actually, let's organize this and say that this is the proof. So here is our proof. First of all, we want to recall what the ring axioms say. First of all, we need both plus and times. They both have to be closed on the set S. Second of all, plus and times have to be associative on the set S. Third, we need addition must be commutative on the set S. Let's see, we also need the existence of a zero that is an additive identity. So we need a 0 sub S inside S such that for all little s inside S, 0s plus S is equal to S plus 0 sub S, and both of these are equal to S. And then finally, well, second to last, we need additive inverses. In other words, for every little guy inside S, there exists somebody that I'm going to call minus S inside S, such that S plus minus S is equal to minus S plus S, and both of these will be the 0 inside of set S. And then the final ring axiom is that times distributes over plus. Now, several of these properties are going to actually be inherited from the ring R, and I want to kind of look at that first. We already know that plus and times are associative on R, so this one is inherited from the ring R. If plus or times was not associative on S, then plus or times would not be associative on R, and R would not be a ring, but R is known to be a ring, so no matter what subset we're in, plus and times are going to be associative. Well, likewise, plus is commutative in the big set R, and so it has to be commutative on S. So this is another one that is inherited from the ring R. Now, in these next two properties, what I want to do is get an idea written down. We already know that if S does turn out to be a subring, that its additive identity is going to be the same as the additive identity in R. So what we're going to want to try and do here is we want to show that the 0 for R actually belongs to S. And for showing additive inverses belong to set S, again, what we want to do is we want to show that if minus S is the additive inverse of little s inside the ring R, then minus S will belong to set S. And then finally, it's worth noting that the distributive laws are also going to be inherited from the superring R. So this is another one that is inherited. If times did not distribute over multiplication on S, it would not distribute over if multiplication did not distribute over addition in S, it would not distribute over addition in R, but we know that R is a ring, and hence the distributive law has to work in any subset of R. So the upshot of this is that we have three main things that we need to worry about. We have to worry about closure. So that's one that we have to worry about. And we have to worry about showing that the additive identity in the big ring R actually belongs to S. And we have to worry about showing that if S is inside S, then the additive inverse of S in R belongs to set S. So we basically have three things to worry about. And the other ring axioms are inherited from R. So let's tackle each one of these issues one at a time. So the first one, plus and times and plus are closed on S. Well, we can do half of this right now, and the other half is going to have to wait for a few minutes. So I'm simply going to make a note that the third property, property C, says for all R in S inside set S, R times S must belong to set S. So we already know that times is closed on S. Now, for the time being, I'm simply going to leave it as a question. Is addition closed? because we don't really know how to answer that yet. What we have to do here, though, is we need to show that for all R and S inside capital S, the sum R plus S does belong to capital S. So we're going to have to put that one off for just a minute. So the second thing that I want to look at is additive identity elements. Now what I know here is I know that S is not the empty set. So I do know that there exists some element A inside of S. I don't know what this element is, but I know that there is an element inside of S. And I know that A also has to belong to R, since S is a subset of R. And that says there does exist a minus S inside capital R with, let me say A here. Got a small little change in stuff. So there exists a minus A in R with A plus minus A, which is A minus A, being equal to the zero element of R. But now let's look at that second property that set S has. So let's look at property B for set S. Property B for set S says that for any pair of elements inside S, the sum R plus minus S is known to be inside of S. Now, this is a universally quantified statement. That's what that symbol there is. And so what we're going to do is we're going to let R be A, and we're also going to let S be A. Then property B says that A plus minus A belongs to S. But we already know A plus minus A is just A minus A, and that's the zero element in R, and that says we now know that the zero element in the big ring is indeed an element of S, and that's enough to say that S has an additive identity element. Well, let's see. The next thing that we're going to be doing is looking for inverses. So at this point, what I need to do is I want to show that if I have some element A inside S, then minus A is also inside S. Now again, we're going to start this off with looking at some things that we know. We've just gotten done proving that the zero element in R does belong to S. We also know about property B. And property B is that for any pair of elements inside S, R minus S will indeed belong to capital S. And again, we're going to use the fact that this is a universally quantified statement, so no matter what values of R and S I pick, as long as they're in set S, I have this conclusion. So what I'm going to do is I'm going to set R equal to the zero element in the ring R, because I know that that zero element is inside S, and I'm going to let little s be my A element, this element up here. So what property B says is that R minus S, which is 0R minus A, belongs to S. But 0r minus a is just minus a, and that means minus a does indeed belong to S. And so what we now have is each element inside set S has an additive inverse living inside set S. So at this point we've shown everything except closure for addition. So I want to make that note. We have all the ring axioms satisfied, except for the statement that says plus is closed on set S. So we now have to actually look at how do we prove closure. Well, the first thing that we want to do is we want to remember what it means when we say that addition is closed. In other words, the first thing that we want to do is we need to show that if R and S belong to set S, then R plus S also belongs to set S. That's our goal. Now I also want to list the things that we already know about how things behave inside set S. Well, the first thing we know is that if S lives inside capital S, then minus S also lives inside capital S. That's the previous part of this proof. We just got done showing that. And we also know property B. And property B says no matter what two elements you pick inside the set, and I actually want to write this slightly differently. Property B can be stated as for any, let's just call them A and B inside set S, A plus minus B is known to be inside set S. And again, this is a universally quantified statement. And what I'm going to do is I'm going to choose appropriate values for A and B. So I'm going to let A be equal to R, and I'm going to let B be equal to minus S. And I can do that because this up here says that if I have S inside capital S, then minus little s also belongs to capital S. So we know that these two things are going to be inside of S. So I want to kind of make that a note. If R and S both live inside capital S, then we already know R and minus S also live inside capital S. So we know that these two elements here do live inside capital S. And now property B kicks in. So property B kicks in. And says that A minus B, which is R minus S, which is the same as R plus S, that has to live inside S. And that lets me say that addition is closed on the set S. And at this point, we now have the fact that S under addition and times satisfies all the ring axioms. And what that says is that S under times and under plus and times is a ring that lies inside of R under the same operations that R uses. And that lets me say that S under its plus and times is indeed a subring of R under plus and times. And that completes the proof of the subring criterion theorem.